So welcome everyone to our March 2018 Statistically Speaking webinar. We are here with Steve Simon, who's going to talk about a topic that I think a lot of us struggle with, which is transformations. It's one of those things we all learn about, but there are so many details about when to use them and when not to, and what they really do and how they really work, that Steve is going to clarify for us. He's a pretty popular guest speaker around here, so I am going to turn it over to him.
Thanks, Karen. And I should mention that Karen had some fairly helpful comments about this presentation, so she deserves some of the credit also. Now, the thing I want to start off by saying is transformations don't always help. And if there's one thing that bugs me about the world in general, are people who sell cure-alls, that it works for everything. Transformations don't always work, but when they do, they often help in several ways simultaneously. So it's kind of cool. And we're going to talk about this in the context of linear regression. But transformations work for other types of tests, of the humble t-test, analysis of variance, even some more exotic things. But I wanted to place this in the context of linear regression because that's a context that a lot of people are familiar with, okay? Let's see what, I always start with a bad joke, okay? And since I'm doing a webinar and you're all on mute, I can't hear you when you laugh or groan or whatever. So I really want you to say something in the chat box or question box or whatever, because that's important to me to know that my jokes are either loved or despised or anyway. So there's a story, and this is not one that I made up. It's one that I found on the internet. So it's after the great biblical flood, and Noah lets all the animals out, and he tells them, go forth and multiply, and all the animals scatter, and they're very happy to leave. But there are a couple of snakes who did not want to leave the ark. So Noah asked them, what's wrong? And the snake said, we can't go forth and multiply. We're adders. All right. So at this point, you're supposed to say ha ha or groan, or that's a corny joke. But there's a second half to this that's important, and that second half actually relates to what I'll be talking about today. So Noah found some driftwood, and he built a piece of furniture for them, and then he said, now you can multiply because you have a log table, okay? Now, this takes you all the way back to your life as a high school student, and some people dreaded the high school math. Some people loved it, some people were indifferent. But the thing about a logarithm is that the log of a product is equal to the sum of the logs, okay? So a logarithm can change adders into multipliers, okay? Sort of. It's I probably have that backwards, but you get the point. Yeah. And we'll be talking a lot about the log transformation because the log transformation is special among transformations, and it's the first one that I tend to look at for a variety of reasons. We'll explain that. We'll look at some other transformations also. And I had to go on to the internet and find an example of a log table. People used to use these things because back when you had to do these calculations by hand, multiplying two numbers together was a slower process than converting them to logarithms, adding the logarithms, and then looking at the anti-logarithm. No one does this anymore, all right, because we have computers, but the logarithms have this nice property of taking something that's multiplicative and converting it to something that's additive, and that's very important for a variety of reasons. Some of you may have seen this thing before. It's a slide rule. Okay. The slide rule also uses logarithms in order to allow you to take a certain amount of distance, add another amount of distance to it, and instead of getting a sum, you get a product. All right, so slide rule is a very easy way of multiplying numbers together. No one uses a slide rule anymore. I was in high school in the 1970s, and they were just starting to be phased out back then. So, man, that's like 50 some years ago. That's pretty frightening. But most of you have probably seen these ancient things, and they're all based on the logarithm. Okay, so you all know what linear regression is. And I'm going to talk about linear regression with one independent variable, but I could have just as easily talked about 2 or 3 or however many independent variables, or I could have put this in the context of analysis of variance or whatever. But the simple linear regression model says y is equal to beta 0 plus beta 1 times x plus an error term. All right, and there are 4 assumptions of the error terms. The error terms, the epsilons, they have to be independent of one another. They have to be normally distributed. They have to have a mean of 0, and they all have to have the same variance. Okay, and you use some calculations. You can do this by hand, or you can get the computer to do it to get least squares estimates. B1 is the least squares estimate of beta 1. B0 is the least squares estimate of beta 0. And they have the following interpretation. B1, it's the estimated average increase in y when x increases by 1 unit, okay? And then B0, the estimated average value of y when x equals 0. Remember that, because these are important, because this will change when you throw a logarithm into the mix. But of the assumptions, sometimes those assumptions are not met. And in particular, the assumption of normal distribution and equal variances is sometimes problematic. So in that case, sometimes a transformation can help. Okay. Now, what does a transformation mean? It says instead of making your dependent variable y, it's f of y. There's another type of transformation that we'll cover briefly. I don't like these, but I want to mention it because it's important. Sometimes you transform not the dependent variable, the y, but you transform the x, okay? And I want to point out that doing this creates a nonlinear function, all right? F is a nonlinear function typically, but it's not the same as nonlinear regression. And nonlinear regression is certainly an alternative that's worth considering in a lot of contexts, but doing a transformation is not the same thing as doing nonlinear regression. Nonlinear regression says y is a nonlinear function of x plus an error term. Okay, and you can't say, well, f is h inverse or something like that. It doesn't work because of that error term sort of mucks things up. Okay, so a transformation is where we either convert the dependent variable y or we convert the independent variable x using a function. All right, so when should you consider a transformation? All right, now quite often you will have inside knowledge that a transformation is needed, okay? So I work with a lot of people who are doing genetic expression data. And it turns out when you're looking at the amount of circulating messenger RNA, whatever that is, and comparing it between cells treated with substance and cells not treated with the substance, those almost always they do a transformation on because we have inside knowledge that that transformation works, okay? And you can find out this inside knowledge just by reading some of the other journal articles that are working in the area you're working in, or talking to people who've done this sort of data analysis for the past 20 years. And they say, oh, we always use square roots, or we always use logarithms, or an inverse transformation makes a lot of sense, okay? So a lot of times we have inside knowledge. We know already what's going to work. Because it's worked before and we expect it's going to work again. But also, you should consider a transformation when you see something wrong in the residual plots.
Looking for practical, relevant answers to all of your statistical questions? Join our Statistically Speaking membership program for the full presentation and access to new live presentations like this one every month, as well as weekly Q&A sessions with our statistical support team. Visit theanalysisfactor.com for details. Happy analyzing!